Hello, thanks a lot for the intro. And just want to mention that if you like the previous talk about mini CPM, we have like some big inspiration of mini CPM in our smol LLM series, so huge shout out to them. So in this talk, I will talk about the training process on small and larger language model. So to do a quick presentation, I'm a researcher at Hugging Face and I mainly work on pre-training. So I think you might all know Hugging Face, at least I hope. So the main thing at Hugging Face is like the transformer library. So basically you can load and train every model. And it's also like the reference implementation for a lot of open weight model. And there is also the hub where you can share models, datasets, app with spaces. And yeah, there is like a few new features that I'm not sure everyone are aware of. So we have like recently this XZ storage, which is basically very efficient and fast storage. And we have this inference provider when you can directly use on Hugging Face and Hugging Face API all your favorite inference provider. So open source is very important, and we also work on like open science at Hugging Face, and they are closely related. And so I will talk about one of the big projects we have called smol LLM. So let's dive into it. So like any good pre-training talk, I'm forced to talk about this chinchilla scaling laws. So basically, the idea of the chinchilla scaling laws is that if you have like a fixed amount of compute, so compute budgets, you can fix the number of parameters and training duration to have like an optimal model. But so yeah, so if you have a 67B model and you should train it on like 1.5 trillion, that's what this little cute chinchilla is saying. But in reality, people are not following at all these rules. So the last llama is trained on 40 trillion token, and the Quen team that gave a talk this morning said that even the 1.6 billion, sorry, not 1.6, but 0.6 billion models is trained on like 36 trillion token, which is like far from chinchilla optimal. So why? So basically, models are still learning after this chinchilla optimal point. So it might not be optimal in terms of compute allocation, but if the only thing you care is not performance, but also usability, you want to train smaller models. You have this plot where basically there is this GPT-4 performance, which is probably in terms of trillion parameter size. And we have this Gemma2 9B, which match this GPT-4 model. So this is pretty crazy. So this is on LM6. This is not perfect benchmark, of course, but this is good enough to measure like the speed of the development of small models. So yeah. At Hugging Face, we also developed the smol LLM series, and we noticed that this is also true at the 3B scale. So a lot of model providers are starting to release more models at like the 3B scale, and we see that they are getting better and better. So this is like our smol LM2 performance. So you can see it was, at the time of the plot at least, state of the art. No, there is like Quen 3, Gemma 3, and stuff like that. But at the time of the plot, it was state of the art. And like the key of all of this is the dataset we also develop and release. So you can see in this little meme, FineWeb2, FineMath, StackEdu, which are very high quality datasets on math, code, and also like web datasets. And so the key is like the quality data, of course, but it's also to train it for very long. So, and we also do this multi-stage training procedure. Basically, the closer you are to the end, the more high quality document you feed to your model. So the big point of it is that everything is open. So the dataset of course are open, but we also release like a GitHub repository with all the training recipe. We have this nanotron library, which is very good to do large-scale training. We have datatrov, which is very good to do data filtering and tokenization. And we have LightEval, which is for evaluation and which is very good as well. So yeah, of course, the model weights are open as well, but that's like just a cherry on the top. We also have this smol LLM, so sorry for the naming, I think this is not optimal. But basically those models are like 360 million and 135 million parameters. And they are state of the art also for the size. When we trained them, it was more like a scientific process, like how much we can push the model to be small. We didn't really think about application, but we will see later that there is, and they are actually pretty cool. So yeah, I mean, later is now. There is some cool application. That's just a few of them. First, we collaborate with this team called NuMine, where basically we did some specialized model for they did. They fine-tuned this smol LLM for specialized model for text extraction. And we also have this demo that was made by our colleague VB. And basically, the idea is that you give a prompt and it's generating like this GitHub issue. And like the cool thing with that is running totally on your browser. So there is no inference to a third server or thing like that. Yeah, I didn't talk about it because it's obvious, but the big plus is that you can run it on a device. You can run it on your Mac, iPhone, but you can also run it on your browser. Yeah. So there is also some cool little application, such as like using pip install to use a LLM or chat like in a PDF with your LLM. I'm not sure if the security team will be happy with that, but it's pretty fun. And there is also the simple or not function calling that is cool. So one great thing is that at Hugging Face we have multiple teams in this science team, and so we developed the smol LLM series, which is text only, but there is other people that develop like a multimodal version of it, and also a robot team that help develop like the best small model for each domain. One of the very cool projects, and I particularly like this one, is the smol VLM. You can see like the true application of our smol LM text model is basically to have like a pretty good smol VLM, so vision language model. We also gave it like the video capacity with smol VLM for videos, and yeah. So this plot is quite funny because there is this idFix model which was state of the art like 2 years ago, and now this model was like 80 billion token, and now with like only 256 million parameters, we can achieve the same performance on this benchmark. So this is like very quick mention, but our robotic team is also working on a smol VLA, so vision language action model, and it's still in progress, and you will, I hope, probably hear about that as well. So the pretty cool thing is that we can intervene like in the pre-training as well, not only on fine-tuning, so this is pretty cool. So, you hear me saying a lot small since the beginning of the talk. We can ask like smol LM how much I said small, but I will now talk about like bigger models. So the main thing that is constraining us when we are building big models is the compute bottleneck. So basically, we are compute bound because we are not like OpenAI or NVIDIA or whatever big labs, and we need to collaborate with other people that have some GPU idles to train like bigger models. One of the great techniques that was developed by Google DeepMind folks is this DLOCO techniques. So basically, if you know federated learning, it's pretty similar. If you don't know, it's okay. But the idea is that you have multiple workers and you train independently each worker, and then you synchronize the gradient every edge step. The algorithm is actually quite simple. You have this inner side where you train your model with like an inner loop using Adam W, and you have this outer optimizer using this good old Nesterov stochastic gradient descent. There was this report, an open reproduction of DLOCO called Intellect 1 by the Prime Intellect folks, and basically they managed to scale it in the open. And at Hugging Face, we try to do, or at least we have a project to do the same thing and scale it even more. So the goal is to extend like this smol LLM recipe, which is working at small scale, and like scale it to the 70 billion, 100 billion, I don't know, on like a lot of tokens. So you can also see on these plots, I mean not plot but meme, that there is also some medium size that are cooking at Hugging Face. Can be smol M3 or smol MOE. So yeah. So that was like a quick presentation of the work we do. Now I want to like explain you what's the day-to-day of a research engineer working on pre-training. So I will take the use case of like a few, I mean 1 month ago from now, where we try to change the optimizer of our model. So basically people have been using Adam since 10 years. That's quite a lot. And every time there was a new optimizer, the community like were hyped and people didn't end up using it. A good example of this is to look at what bigger labs are doing. And basically everyone is using Adam. So that's kind of sad. Even Llama 4 is using Adam. But we have some insights that people like at Google, XAI or OpenAI, Anthropic, we don't know, are using something different than Adam. So the process to do that is, of course, to talk with researcher, go on like HF posts, papers, blogs, or Twitter, or X, whatever, to search all of that. So I'm gonna try to explain you why, what are those new optimizer based on. So you have this new paradigm. So you will see the naming are pretty funny, but you have this new paradigm. So basically, you are before doing this your classical update state, you are multiplying your gradients by a matrix, and this matrix, this p-1, is called the preconditioner. So because it's like preconditioning the gradient. There is many algorithms that are using that. A few of them are shampoo, soap, sillon, and a lot more. And the one I particularly like is an algorithm called Mu, and it was developed very in the open by Keller Jordan and a lot of other people. And basically the idea is quite simple. So you have your gradient, and you apply this function called Newton-Schultz. And this function is basically orthogonalizing your gradient. So you project your gradient into a space which is orthogonal. And this is nice because it has a lot of properties that are cool. So yeah. The one nice thing with this is that this Newton-Schultz method can be done in low precision. So it's very fast, it's memory efficient, and also it's just matrix multiplication. So there is some consideration with like 4D parallelism, stuff like that, but we will skip that. So when developing that, we need some people to do the job and pre-train model to know if the model, if this optimizer is good or not. And that's what people at Kimi did, and they released this MOE called Moonlight, and a paper saying that the Mu optimizer is basically better than Adam and more efficient. Yesterday, there was this company called Essential AI, which Vaswani, which is like the main author of like Attention is All You Need Is In. And they are basically releasing a paper that, so it's just today, so you don't have time to read it fully. But the idea of the paper is to show that Mu is effective. You can scale the batch size, which is pretty cool when you are doing large-scale pre-training. And it also works with this obscure method called MuP, which allows you to transfer hyperparameters from a smaller model to a bigger one. So there is also this other optimizer called Ademamics. This one is very simple if you know Adam. You just add this M2 momentum, which is basically tracking the old exponential moving average of the gradient. So at a step t, you are looking like far back to have this gradient, and this is like tracking this quantity. When considering new methods like Ademamics, you have to think about everything. And one thing is the learning rate schedule. So we are using this WSD schedule that MiniCPM introduced in the large language model space. And we tried it, and we basically use it everywhere now. And it's as performant as GOSIM. But there was some consideration, because when you are using WSD, you have this decay phase, which is quite important. And with Ademamics, there is a chance that the decay phase, which need the recent update of the gradient, interact badly with this old EMEA tracking like this old gradient. So this is something that we have to be careful of. And I'm talking about this because I want to explain that when you are working on deep learning, everything is interacting together, and this is like my life. So yeah, everything is like interacting together, and you have to be very careful when you change hyperparameters and how they interact together. So let's get back to Mu. I talked about Ademamics and Mu. Why not mix them together? I mean, why not? So that was an idea. So I tried this as well. So this is something to try. I named it Ademamiu. This is very bad naming. Please suggest a better one. But yeah. There is also this thing called learning rate scaling and MuP that I talked about previously. So you multiply your learning rate by quantity, and this quantity differs from what some of the Mu authors are saying and what the Kimi team with the Moonlight paper is showing. So this is quite different. So this is something like if you want to try new optimizer, you have to be careful of. So one of the approach is like to do very rigorous experiments, only change one hyperparameter at a time, and this is what you're supposed to do. But sometimes you have some spare compute, and this is late at night, and you need to use those GPUs. So you just run a bunch of YOLO run, and you hope for the best the next day. So this is some real message that I sent our Slack at Hugging Face. So we were running a bunch of experiments, and basically you go to sleep, and you don't know what you are waking up to the day after. So you are hoping for the best and expecting the worst, of course. But sometimes it's even worse than what you expect. So this is also a real plot that we had. So yeah, this is like the loss. You see those low spikes. This is not normal at all. Basically, when you have that, you cry. There was also this fun moment where basically our grad norm was making a M, like the M of Mu, which is like the new optimizer we were trying. So we were joking inside the Hugging Face, and like, yeah, the model is talking to me, is making a M because I'm using the Mu optimizer. Okay, whatever. So this is quite fun, and this is like our day-to-day. So with all the divergence, everyone was sad. We didn't understand what was happening, and yeah, and like, so this is the end. No, of course, this is not the end. A few weeks later, 2 weeks later, I said, I'm not sure about this number. There was some issue with our current training, so we started training without this new optimizer because we thought it was wrong. And yeah, there was some issue we don't really understand. So basically, all the Muon experiment was like in about 2 weeks or something like that. And we have to move on. Like if it's not working, you have to search other thing. So we moved on, do some other thing, and start like the training. And to explain the bug we had, I need to talk to you about our beautiful library called Nanotron and the distributed learning. So we have this ultra scale playbook, which I strongly recommend. I think this is like if you want to learn about how to like scale LLMs on GPUs, this is the best place to start and also to become an expert in. So yeah. And there is this notion called tensor parallelism. I will not explain in depth, but basically you have your matrix, you split it in two, you put one part on one GPU and you put another on the other GPUs. So your matrix is split between two GPUs. That's like the K2 and the K1, for example. And the issue was pretty dumb, to be honest. It was very simple, but very hard to debug. And the issue was basically that we initialized the same way. So there was like the exact same weight for K1 and K2. And there was this like weird symmetry that was introduced by this that probably is the reason why our previous run are diverging. And yeah, so we fixed it. We resumed the current training. It was working well. We didn't have time to make the experiment at the same scale. But I also want like so it's too late for this training to use this fancy optimizer. But we can go back to the result we had at like a smaller scale. This is like the 1.7B scale. And we can like see the results. So this is like, so this is a bit messy, but this is like all for a bunch of runs, not all at all, but like a selected one for the 1.7B scale on 100 billion token. And you can see that the best optimizer at this scale and in this setting is this new Adema Muon stuff, whatever. So, I mean, it's pretty cool. I think it's probably working well. We need to try it more. We need to tune more hyperparameters. We need maybe to have like a stronger baseline. But this is like very, very cool. So yeah, maybe a closing remarks is that all of this is possible because of open science. On this plot, you have basically the timeline of the development of Muon. So it started with GPT-2 because it's like basically André Karpathy did this video reproducing GPT-2, and it gave like an idea to this researcher called Keller Jordan, which is now working at OpenAI. And he developed this modded GPT repository and developed this Muon algorithm. And then you have the open source lab, such as Kimi, such as Essential AI, and other labs as well, that, as Microsoft, for example, that basically took this Muon, improved it, find some cool stuff, and release the papers and all the artifacts that lead to that. Also, the Nano GPT, there was some extension. There is this Nano MOE by someone on the community. There is this Nano DLoco, so basically you can speed run and try to achieve the best loss possible with DLoco. So this is the method I talked previously. And we have this Nano VLM, so we just released that at Hugging Face yesterday, which is basically a very simple reproduction of the training pipeline of a vision language model. Yeah. So yeah. Okay, so stay tuned for like all the cool stuff I talked about, which is like the Boom, smol M3, smol MOE. And you can follow us like on the hf.code at Hugging Face TB. So yeah, thank you.